Swayam Prabha. Digital India. Educated India.
Okay, good morning. We are now on to lecture 4 in the first module, which deals with the review of basic structural analysis. This is the first of 7 modules, and in this module we will be covering work and energy methods. In the last class we covered statically determinate structures. Now this slide shows the summary of what we do in structural analysis. We try to find the response of a given structure subjected to given loading, and we are interested in both the force response and the displacement response. We will now look at an energy formulation, virtual work formulation of finding these two responses. So to find unknown forces in the force field which satisfy equilibrium, we can invoke the principle of virtual displacements, and to find unknown displacements in the displacement field, we can invoke the principle of virtual forces. To begin, this slide shows what we mean by coordinates, how we use these coordinate indices to identify external joint forces and joint displacements. Fj and Dj are the respective joint forces and joint displacements in a truss at the pin joint. Some of these forces could be reactions, and the corresponding displacements would be arrested. The rest of the joint forces would be direct actions, loads. The directions of those loads and the locations are marked, and from the internal side you have bar forces Ni and corresponding bar elongations Ei. The bar elongations are related to the joint displacements through relationships called compatibility, and the internal forces in the various bars are related to the external joint forces through equilibrium. So the force field must satisfy equilibrium, which means it must be statically admissible, and the displacement field must satisfy compatibility, it must be kinematically admissible. So here is a very useful principle called the principle of virtual work, originally discovered by Bernoulli. In its original form, it actually dealt with the behavior of a rigid body. You see here a rigid body subjected to various external forces. We could resolve all the external forces to a resultant force, and if that resultant force is equal to 0, we know that the system, the structure, the body is in a state of static equilibrium. What Bernoulli suggested was to give a very small displacement to the whole body. It's an imaginary displacement, it's a virtual displacement, it's a displacement to be given in such a manner as to not to disturb the force field, and if you find out the delta components, you have F1, F2, F3, F4, that is the change in position of the points of application of the various forces, and if you do a scalar product of all of them and add it up algebraically, you get the total work done on this body, and that total work done must actually, it's a dot product of the force and the displacement vectors, that must be equal to 0 if the body is in equilibrium. It easily follows from this. Now, although this was originally proposed for rigid bodies, this can also be applied for deformable bodies, and all our structures are deformable. If you go back to the earlier problem of the truss, we can actually extend the principle of virtual work to a more expanded and diverse application, where we can even visualize two identical structures, and we look at the force field in one of them and the displacement field in the other. The advantage of looking at it this way is you remove the cause effect dependence between the force field and the displacement field. Let us call the first field, where we have a statically admissible force field, as system 1, and the other system, where we look only at the displacements, as system 2, where we have a kinematically admissible displacement field. So in this field we look at the dj's. In this particular example, you have 14 values of dj, and you have 11 values of ei, because there are 11 members, and they are all interrelated, bound together by compatibility. The compatibility ensures that the whole truss is held together. You do not have any separation of any joint from any member at any location. And in the first field we have 14 values of the joint forces Fj and 11 values of the bar forces Ni, and these two are also interrelated through equilibrium relationships. Now you could have a situation where there is a cause effect relationship between system 1 and 2, but that is not necessary for the proof of this principle, and so this is a powerful principle, and we will accept it for the time being without any proof, which says that if you were to multiply Fj with dj, and you do it so that you have a conjugate product of Fj and dj, Fj and dj are at the same location pointing in the same direction. If one points in the opposite direction, you have a negative value of that scalar product, and if you do an algebraic sum over all the joints, in this case 14 joints, you get a product which has a units of work, but it is appropriate to call this as virtual work, an external virtual work. It is virtual because it is not real, you are just multiplying two numbers, okay. There is some commonality between those numbers, but there is no relation, no cause effect relationship, and the sequence of loading and all do not come into this, which would come in an energy formulation. So that is the advantage of a virtual work formulation. Now if you take the internal field, the internal forces Ni in system 1 and Ei, corresponding Ei in system 2, and do a product and an algebraic sum, then you have the internal virtual work. Now these two numbers, they have units of joules, will be exactly equal, and there is no requirement that the structure should behave elastically. You can use this for even nonlinear behavior, for even plastic behavior. The only requirement is that the force field should satisfy equilibrium, the displacement field should satisfy compatibility, okay. And the joints can also move. You can see here the entire system is moving, the supports can also move, but the internal integrity of the structure should be preserved. Is it clear? Now we will show a simple validation of this theorem, because it is a powerful theorem. Let us look at one bar. Let us look at it at system 1, where you have a statically admissible force field. So you have forces F1 and F2, and you have an internal force at any location n. Theoretically that force can change along the length of that bar, n of x, and simple equilibrium demands that for the overall free body F1 and F2 must be equal and opposite to each other, and the internal force in that bar must be a constant and equal to this external force, and let us say that force is p, so n of x is constant, it is equal to p. This is the complete information as far as the force field is concerned. And if you want to express in terms of boundary conditions, the axial force, the internal force at x is equal to 0 must be equal to plus F1, and the internal force at x equal to L must be equal to plus F2, and F1 and F2 must be numerically equal to each other. Now let us look at another field and completely independent field, the same bar, and we are looking at the displacement field here. So let us say that the left end of that bar moves to the left by an amount d1, which is conjugate with F1 but not related to F1 by cause effect. Similarly, the right end of that bar moves to the right by d2, which is conjugate with F2, and let us say any point in that bar located at x moves actually by a distance u of x. You know, commonly we use u v w in the Cartesian space system to relate to displacements in these three directions along x, y and z. And let us just take some random variation in u. Let us say you heat that bar and you have a different temperature at different locations, it is possible to get this kind of variation. Okay. So the compatibility requirement is that you must not have a break in the bar anywhere, which means that curve should be continuous, and there must be a compatibility relationship of u at x equal to 0 being equal to minus of d1 and u at x equal to L being equal to plus of d2, right. So this is a complete displacement field, it is kinematically admissible, and we will check out and see whether the principle of virtual work operates here or not. So this is the external virtual work product F1 d1 plus F2 d2, and how do you write the internal work? You can't write it so simply, because at every location x the value of u of x and n of x both can change. So you have to do an integration, you have to take a small element dx and it will look like this. Now work is given by the axial force n of x and the change, the local elongation at that point, which comes when you integrate the strain, right. The strain is u dash of x du by dx, and so this is the expression for the internal virtual work, and if you invoke the expansion of that integral, you can, and you apply the limit 0 to L, I think you are familiar with this, it will take this form, right. You have NL UL minus n at 0 with u at 0 minus integral u dn. Now because there is no change in n along the length of this particular bar, that last quantity is it will vanish, it is equal to 0, and if you now apply the boundary conditions of n of L, u of L, n of 0 and u of 0, you will find that you get exactly the same expression as for external virtual work. This is a beautiful validation. You can see clearly there is no relationship between the axial force distribution and the axial deformation distribution, and a similar proof is possible for when you bring in bending and axial forces, bending and shear forces. The proof is available in the book Structural Analysis. Now let us apply this principle. You are familiar with the unit load method, and let us use it first for finding an unknown displacement. What we traditionally do is we apply a unit force in the direction and at the location where we want to find the displacement. So if you want to find dj, you have to apply fj, and it is convenient to apply fj equal to 1. So you have a geometry problem, you have a real displacement field, and you are creating an imaginary force field which you can analyze. In other words, you are using statics to help you solve a problem of kinematics, okay. And we are using the principle of virtual work because we are using the work as a bridge that connects the force field with the displacement field. Now if you do this product, you will get 1 into dj as the total external virtual work, because there is no other joint, no other force acting which moves, and the total internal work is Nij. Now that small Nij is defined here as the axial force in the element I caused by Fj equal to 1. Okay, so that is a notation we will use consistently, and Ei is the elongation in the ith bar. Is it clear? Those arrow marks should make it clear. If you look, yeah, this is Nij in the ith bar, this is Ei in the ith bar, and we are just multiplying them for all the bars and summing over I, and it does not matter what caused the displacement. If the displacements were caused by the application of loads on the truss, then you can get the bar elongations from the actual forces in that real truss by multiplying Ni with Fi. What is Fi? It is the actual flexibility in the truss, and we have already seen this Fi is equal to Li by Eai. We assume that all the bars have the same material, so the E value should be common. If it is not, you can account for it, and so you have this formula dj is equal to Nij Fi Ni. So the original formula is 1 into dj, and it is important to remember this, because sometimes people remember only the formula and then you run into problem of dimensional non-homogeneity, because you will find that the right hand product does not really match in terms of units with the left hand product. This is a big picture, and you can apply this to find any unknown displacement, or you could use it to find a flexibility coefficient. We will see this later, and you can have two kinds of problems in which you just have a geometry change caused by an environmental effect like temperature change or a lack of fit in a truss, or you could have it for the more common application of finding an unknown displacement in a loaded structure. Now if you are finding the unknown displacement in the loaded structure, here we are making the assumption of linear elastic behavior, because the modulus of elasticity comes in here, and so you will get this form for a truss, and you can now pull out the definition of flexibility coefficient from here. Fjk, how would you define Fjk? Fjk is defined as, is it a force or is it a displacement? This is a flexibility coefficient. So flexibility coefficient is a force or a displacement? It is a displacement. So this is the displacement at the joint coordinate j caused by, due to the application of a unit load at the location k, and at all other coordinates, let us say L not equal to k, there should be no load. So there should be only one load at a time, and while we are at it, we will also define the stiffness coefficient. We will be coming to this again and again, so might as well look at it now. We use the symbol k to refer to the stiffness coefficient, and let me take j, but I will avoid k because there is a duplication of those units. So I will say JL, let us say. Okay. What is this? This is the force at the location j due to a unit displacement. So here we have a unit load or unit force, whereas here we have a unit displacement at this location. So this is unit, and that displacement for a truss is a translation, but in a beam you could have a rotation. and it is complete only if you take other joints, let us say M not equal to L. So all other displacements should be arrested, which means you are dealing with a somewhat different structure. The important point to note in all these notations is this is the effect, this is related to the effect and this is related to the cause. You get this displacement because you applied a unit load here. Similarly here, this is the effect and this is the cause. Is it clear? Now is there a relationship between these two? Is it right to say that the flexibility coefficient Fjk for a given structure is the reciprocal of let us say Fjl of Fkjl? Is this right? That is what one of you suggested. Is it right or wrong? After all, we have been told that one is the reciprocal of the other. Is it true? This is not true. Why is it not true? This is wrong. What is true is that the flexibility matrix is the inverse of the stiffness matrix, and that does not mean this. So we will study this in more detail in the next module. Okay. Right. So this can be applied to finding trusses. So here is an example of indirect loading. Let us say you have a lack of fit and two of the bars have a change in length. The bar number 6 has been manufactured and came with a length which is 5 mm more than its desired length, and the bar number 9 is too short by 3 mm. So you kind of fit things together. Will you get any internal forces when you do this? No, because you have a just rigid system. The bars will just move about a little bit, there will be no support reactions, no internal forces. But if the structure was over rigid, it is possible that you have support reactions, you have a self equilibrating system, right. Now the question is, can you find the horizontal deflection D11, is it D11? How much will that joint move to the right? This is D11. So how do you find out? Apply a unit load exactly there, analyze the system. When you analyze it, you will quickly realize that if you put a unit load there, you will get a unit force in the bottom 3 bars, you will not get it elsewhere. So it is very easy to analyze, and you invoke the formula 1 into D11 is equal to the total internal work. The internal work relates to only the bottom 3 bars because all the other bars do not have any force, and actually it works out to the sum of the elongations in those 3 bars. It makes sense, that is how the roller support will move, very easy to calculate. And if you have another example where the problem is you are given a truss with some actual loads on the truss, say a 50 kilonewton load in the middle and 40 kilonewton horizontal load, you need to first analyze this truss, find the bar forces, then for each bar find the bar elongation by multiplying each bar force by its flexibility, and so that is easy to do. Now you do not need to go through the full exercise because only 3 bars really matter here, because all the other bars, you see, finally you need to multiply with this, this and this, because all the others do not have they do not have any force, Ni. So if you want to do it fast, you just find the forces in the bottom chord and you can do that. Let us say these are the answers, then you can just multiply each of those by 1 and the flexibility value, and you will get the answer very easily. Is it clear? So it is a simple demonstration. You can also apply this to beams and trusses. Okay, so I think that heading, this This is something we have finished. Yes, let us apply this to beams and frames. So let us say you have a bar, you have a cantilever beam and that beam bends for some reason. Okay, let us say it is bent because the temperature at the top is less than the temperature at the bottom and you have a linear gradient in the temperature, so it will naturally take that curvature, right. The question is, can you find the vertical deflection? Is there any method that you already know other than the virtual work method where you could solve this? You can use energy method, we have not yet touched. Conjugate beam method, because you remember on the conjugate beam the fixed end becomes free, the free end becomes fixed, and what is the loading you put? There is no bending moment here. So that is how students normally remember. They remember you have to put an M by EI diagram. No, you have to put the curvature diagram. If the curvature is caused by bending moment, you put the M by EI diagram. If it is caused without the bending moment due to environmental change, then you put the phi diagram, the curvature diagram, which is 1 by the radius of curvature. Is it clear? So if the radius of curvature is known, then that is what you put. So you can do the conjugate beam method, but let us invoke the principle of virtual work. And please note, in these applications we use the word principle of virtual forces because your force field is virtual and you are imagining, you are constructing, you are cooking up an imaginary force field to help you find an unknown displacement. So what do you do if you want to know the vertical deflection upward? You put a unit load exactly where you want the deflection, draw the bending moment diagram, and we use the notation small m just as we use this notation small n earlier. Small m1 means bending moment at the location x due to Fj equal to 1, and this diagram is very easy to construct. And then you invoke the principle of virtual work. The external virtual work is straightforward, 1 into dj. The internal virtual work is actually a product of moment times rotation, but since the moment is changing from point to point, you need to integrate and you have to find the change in rotation. Change in rotation is given by d theta. D theta is given by curvature, right. So that is what we do. So that is the integration we need to do, and you can do the integration. In this case it is straightforward. If you take x from the right to left, it is convenient. The bending moment at any location is x and the curvature is 1 by r, it is a constant. So you are actually multiplying a triangle with a rectangle. It is very straightforward, you get the answer. Now let us take the same problem and imagine that this has happened because you applied a concentrated moment at the free end, agreed. So it will lift up. So now the cause is not environmental change, it is a deliberate action caused by a load. Then you get, then the curvature 1 by r is given by what you said earlier, it is bending moment divided by, yeah, the bending moment is constant everywhere because it is a case of uniform bending, pure bending. You get exactly the same answer except that instead of 1 by r you will write it as m naught by ei. Is it clear? So simple. So you have two kinds of applications, one where it is a pure geometry problem, there are no forces involved. Second, you might tend to get confused, there are forces involved, but those forces, you are looking not at the force field, you are looking at the displacement field. It is still a geometry problem, an unsolved geometry problem, but you get some parts of that displacement field. For example, here the rotations, the curvatures, and there are some parts which you do not know like the joint displacements, and to find the unknown joint displacement you are invoking the principle of virtual work. So for beams and frames this would be the formula that you would use. If you want to find dj, the displacement or deflection at a coordinate j, then it is integral mj phi x dx. If the phi is caused by a bending moment, then it is m by ei. Very simple, straightforward. and you could, if you look at it carefully, you are really multiplying two diagrams. You are multiplying a curvature diagram which is real with a moment diagram caused by unit load which is virtual, and if you look at that integral you can see that it is really a volume, and you can invoke what is called the area multiplication method by taking a slice of that volume. You will find that the local elemental volume is dV is mj x into phi of x into dx. It is very easy to understand this, and actually you are integrating over the length of that element. Is it clear? So you can do this. You can do it in a simple way. If you have laid down the curved portion, you see the interesting thing is one of those lines will be straight. Which one will be straight? Mj will always be made up of straight lines, because in a beam when you apply a unit load you get a straight line bending moment diagram. Mj is always straight, so it is necessary to realize that your ordinates should be linear. So put that on top, and the curved diagram which comes from the curvature could be straight, could be curved. In general it is curved. Put that on the ground, lay it down flat, take that area, find out the location of the centroid of that area, and the ordinate of m of j, mj at that location is the average height. So you can reduce this problem to multiplying the area of the curvature diagram by the height at its centroidal location, and this gives you quick solutions. And there are many examples, you have studied it last semester. One of the most common examples is when you have to multiply two trapeziums. Let us say the curvature diagram is also a linearly varying diagram, then you can either, then it does not matter which you put on the ground, because you will get an accurate answer either way, and this is the solid that you get. So the formula you have to remember when you deal with a situation like this is V is equal to L by 6 phi 1 into 2m1 plus m2 plus phi 2 into 2m2 plus m1, which is easy to remember. In case you forget and you flip it over, you will still not make a mistake. It is L by 6 into m1 into 2 phi 1 plus phi 2 plus m2 into 2 phi 2 plus phi 1. This is a very useful formula. It works even if some of those values are negative. Okay, so the trapezium, as long as you have one equation for that trapezium, it will work. If it's one of them is a rectangle, you don't need to use this formula. If one of them is a triangle, you don't need to. You can have simpler methods. So let's take just one example and see how it can be applied. This is a little difficult. It's a simply supported beam with an overhang subjected to some arbitrary loading, and the question is, can you find the deflection at the free end? Well, you have to draw the bending moment diagram, and it is good to separate out the curved part from the straight part. There are some shortcuts involved. I suggest you go through it carefully. We have done this last year, and once you have got that capital M diagram is the bending moment diagram in the real beam, but we are not interested in that capital M diagram. We are interested in the curvature diagram, which is the M by EI diagram. So once you have capital M, if you divide by EI, you got the curvature. To find the unknown deflection at D, you need to apply a unit load, F1 equal to 1 to find D1, and when you do that, that diagram is made up of straight lines. That is your M1 diagram, and this is what you need to do. You need to find delta by multiplying that M1 diagram with a capital M diagram. It makes sense to separate out the curved part from the straight line part, and if you work this out using the formulas we derived, you will get the correct answer. But just to go through this once again, this curved part has a maximum value in the middle of 27 kilonewton meter. It is a parabola, so the area of the parabola is 2/3 that of the equivalent rectangle. This length is 3 meters, so it is 2/3 into 27 into 3, that is the area. Its centroid is at this location where the ordinate here is minus 0.5, so we multiply by minus 0.5. Then you take this difference is 124. So, this triangle is, area of the triangle is half into 124 into 3. The ordinate of this, the centroid of this is at a distance of 2/3 from here. So, it is 2/3, it is into minus 2/3, you can work it out. You will find that the value here is minus 2/3 and so on and so forth. So, you need to complete this product. Be careful, just look for equations. If you have a single equation for a certain length and you are multiplying with another equation for that entire length, you can do it together. But if you have a break in the line, then you must restrict the integration to that region where you have the change in slope. So, you work this out, you can get the answer. In this case, that is the value that you get. Okay, and if you need to find the slope, you do the same thing, but now you put unit moment, you get this shape, and then you can work out the answers. It is similar, you get something in radians. A more complicated problem is a frame, that is a cantilever frame. The question is, can you find D1 and D2? Okay, you have done this last semester, so I will just go through the concept. What do? We first generate the bending moment diagram, and doing this needs some skill which you should have got by now. You must know how to analyze statically determinate structures. Draw the bending moment diagram on the tension side. Again, to find D1 and D2, we are not so much interested in the bending moment diagram as in the curvature diagram. So, if you divide this by EI, you have got the curvature diagram, and the formulas to get D1 and D2 emerge from the unit load method. So, first to find M1, you apply F1 equal to 1, you need to draw correctly the small M1 diagram, which is caused by the unit load. It is a virtual force field, and to get M2, you have to apply F2 equal to 1, you get another diagram. Once you have got these two diagrams and you have got capital M diagram, it is a question of integrating, but you will find it is much easier to do the area multiplication using the volume integral. So, let us take the first case. On the left side you have the capital M diagram, on the right side you have the small m1 diagram. You need to multiply one with the other. In this case both are made up of straight lines, so it is very easy to do it. So, I leave it to you to work out the calculations. You can use that formula for the trapezium and you will get the answers very quickly. Okay. So, that is the first deflection. For the second one, M2 will change, you repeat the same process, you get the horizontal deflection. So, this needs some exercise. Once you practice for a few problems, you will be very comfortable doing this. So much for principle of virtual forces. What was the purpose of principle of virtual forces? Mainly to find some unknown displacement in the real displacement field. Now we look at a less used version of the principle of virtual work. The Bernoulli's theorem originally dealt with this. Here we are looking now at the force field, which is statically admissible, and you want to find out some unknown quantity in that force field. You might ask, why should we struggle and do all this? Why do you need to use kinematics to find a static solution? Can't we do it directly? Yes, you can. If the system is statically determinate, you can directly invoke equilibrium, but you will find there are some situations, for example situations where you have multiple internal hinges, you will find it is much easier to invoke this principle. It is also called the dummy displacement method, but you could call it the unit displacement method. It is like the unit load method when you put that dummy value equal to 1. So, here let us say you want to find an unknown force, or you want to find a stiffness coefficient. Let us say you want to find Fj, you want to find the support reaction in this truss when it is subject to this kind of loading. What you do is you give it a dummy displacement dj equal to delta, it will rotate about the left support. So, you have rigid body movements, and so it is possible for you to figure out how much those locations where 1, 2 and 3 are applied, how much they will move, and once you know those values d1, d2, d3, you can invoke this theorem. They are rigid body movements, so it is easy to calculate. The total internal work in such problems turns out to be 0. Why is it 0? Yeah, because since you have rigid body movements, you do not have internal deformations in those bars. So it is 0 because the internal displacements in the displacement field is 0, not because there are no internal forces in the real force field. Is it clear? And you invoke this, you can solve this problem easily. Okay, so let us demonstrate this with a problem where you have an internal hinge. Okay, so at the left edge, it is not shown. At the left edge, you have a fixity. Okay, in this figure, please note there is a fixed end support at A, and you want to find these reactions. So what you do is, what you see on the right side is the free body of the force field. The force field is real. If you want to find the left reaction VA, what you do is you lift it up by delta, but lift it up in such a way that the fixed end moment at MA does not do work, so it must remain horizontal, and you will find this is the only way you can draw the deflected shape. This is visualizing the deflected shape, and then if you want to find the moment at MA, you give it a rotation theta, but you should not allow any other movement. So please note, when you invoke the principle of virtual work, there should be only one unknown at a time, which means the other forces should not do any work. That has to be done cleverly, and then if you invoke the theorem, it is very easy to compute the reactions. You can also do it in a truss. Let us say you want to find the reactions in a truss, this particular example. If you want to find, this is a tricky thing, not the reactions are easy to find. I want to find the actual force in AB. What should I do? Well, I should now have an elongation in that member AB, and so if I have an elongation in that member AB, this is the way to do it. You will find that let it elongate by delta, but then if I keep this B here, I have a problem because I will also be elongating the bar 2 BC. I do not want that, so I want BC to remain unchanged in length, and so it means I take C at center and draw an arc or a tangent. For small deformation, the arc can be replaced by tangent, so B moves to B dash. So in this configuration, the advantage is the only change in length is in AB, and it is equal to delta, and you have to work out the trigonometry part of this and find out how much has the joint C moved horizontally and vertically. This can be done. Once you have done this correctly, simply invoke the theorem, you will get the answer. So it is a powerful technique. You might make mistakes if you are not careful with the trigonometry involved. Last application, finding a deflection in, okay, I want to show you that this can be also applied to statically indeterminate problems, finding deflections in statically indeterminate problems. So here you have a fixed beam, and the question is, can you find the maximum deflection at the midspan in this beam? So what do? So first of all, you need to have the curvature in this system. So you need to know the fixed end moment. You can use the conjugate beam method and find the fixed end moment. What is a fixed end moment? Q naught L squared by 12, right? So I have separated out the distributed load effect and the fixed end moment effect, right? Now to find, so the M diagrams look like this. You have a parabolic sagging bending moment diagram, Q naught L squared by 8, and superposed on that you have a constant hogging moment, which is Q naught L squared by 12, right? Now to find delta in the middle, what should we do? What should we do? Which theorem will we invoke? Which principle will we invoke? Principle of virtual work or principle of virtual? You can do conjugate beam method, you are right, but we are now on the topic of principle of virtual work.
Virtual force.
Virtual work, virtual forces or virtual displacement?
Force.
Virtual forces, because you have to, so what will you do?
You apply a force.
This, what we have here is a real displacement field. If you divide m by ei, you've got the curvature diagram. What you need to do is a virtual force. This is what you should do. This is what everybody does. But there's a problem with this. The problem with this is you again are dealing with a statically indeterminate structure, and you need to spend some time to figure out the small m diagram for this. Is there a way out which is easier? And this really brings out the power of the virtual work. Is there an easier way? Yes, and I want you to see this. Let's say the degree of static indeterminacy of this structure is 2. Okay, let me treat the cantilever as the primary structure, and why can't I take any values of x1 and x2 here? I can, because if you recall the proof or the origin of the principle of virtual work, the only requirement is that the force field is statically admissible. Now in a statically indeterminate structure, how many force fields can you generate which are statically admissible? Infinite. Only one of them will be exactly correct for the boundary conditions that you've given. So the unique solution is one which also satisfies kinematics, right? But we are not interested in finding the kinematically correct solution also, because here this is just a device to help us find an unknown deflection, right? All we need is any statically admissible solution. So you will find that if I conveniently take x1 and x2 equal to 0, I have got a cantilever. I have reduced that fixed beam to a cantilever beam with a concentrated load in the middle, right, unit load, for which the small m diagram is child's play. It is a small triangle, right, it is a small triangle, and it is minus L by 2. Now will you try this out on your notebook? Can you get the deflection at the midspan? Can you get the deflection at the midspan? I will help you. Just check out this solution. You are multiplying this triangle with these two diagrams, right? One is a parabola and one is a rectangle. Let us take this area. This area, what is the area of the parabola? Oh sorry, let us do this rectangle first. So you are multiplying this rectangle with this triangle. Do you agree that the area is half into L by 2 into the ordinate, because you can take that full area of that triangle and any value of the ordinate here. Do you agree to this part? Now we need to multiply this parabolic area. What is the area? 2/3 of q naught L square by 8
into L
and into L by 2 into L by 2. So L by 2 is outside here, and its ordinate will be located at a distance of how much? So you know that if I have a parabola like this, the centroid will be located in such a way that these distances are, if this length is L, or let us say A, how much will this be? Yeah, it is 5 by 8 A and this is 3 by 8 A, right. So that is how you get the ordinate in this triangle as 3 by 8 of L by 2, agreed? 3 by 8 of L by 2. Now you must be careful about the signs. This product will be negative because you are multiplying something positive with something negative, whereas this product will be positive because you are multiplying a negative with another negative. Clear? Now just check this out. The answer is 1 by 384 q naught L squared L raised to 4 by EI. And just pause for a while and see, if the beam is simply supported, what is the deflection at the midspan? You've done it. It's 5 by 384. So making it fixed, giving it some hogging moment, actually reduces your midspan deflection to 20% of the original value. Okay. in reality many systems are partially fixed, so the answer is between these two extremes. Now what is extremely interesting is you could have chosen any statically admissible diagram. So we will just see an alternative where we will treat the primary structure now as simply supported, okay. That means here x1 and x2 is 0. So now I am dealing with a simply supported beam, and now my small m diagram has changed completely, right. And if I do the multiplication, you can check this out, I get exactly the same answer. This is really a mind blowing discovery. It shows the real power of the principle of virtual work, which means what are the implications of this? You take a complicated structure, a multi-storied frame, if you have the bending moment diagram in any one beam for example, that is enough for you to help you get the deflection in that beam, because you can strip it off from the rest of the structure and make it statically determinate, apply the unit load method. Similarly, we will see this later, you can find the drift in a tall building very quickly by invoking this method. So we will stop here, we will continue in the next class. Some work theorem. Can you just name the work theorems? There are 3 work theorems. Castigliano's theorem belongs to energy methods, work theorems. 3 of them, they are applicable to linear elastic structures. There is Maxwell's reciprocal theorem, then Bette's theorem, no, and Mueller-Brislow's principle. We will see this in the next class. Thank you.